So, good morning, everybody, and thanks to everybody who had a hand in inviting me here, and thanks to all of you who took the trouble to come. It is just amazing to see all these old friends and new friends. So I look forward to sitting and talking and having a chance to hear what's going on in the world. I also just have to say it's just amazing to come to Singapore and see such a vibrant community. It reminds me in a little way of my favorite city, Zurich in Switzerland, and the ETH, the Eidgenössische Technische Hochschule, what was originally just a technical engineering college, which has grown into a world-class university. And the same thing happening here. It's a similar situation. You have a very poor and small country with people who have to work hard to make a living and just have made an enormous success of things. And I just congratulate Singapore and congratulate all of you for doing such a wonderful job. I must apologize for talking about a technical subject. I wanted to talk about my own field and about real science, not just philosophizing. So it'll all be equations, and for those who don't enjoy equations, I invite you to go and enjoy a cup of coffee outside. So here are some citations of the literature. It all starts with this wonderful paper of Bohr and Rosenfeld in the year 1933, which was a very famous piece of work in which Bohr, this was the finest example of Bohr's style. It's a very, very long and complicated argument written in very long and convoluted German sentences. And the unfortunate Rosenfeld had to write it all down 14 times before Bohr was willing to let it go to be published. So it went through 14 versions. And so the title was On the Question of the Measurability of the Electromagnetic Field Strengths. And it's the foundation of the field of quantum electrodynamics. It's the paper in which Bohr found the precise physical basis for the quantum treatment of electromagnetism, showing that just if you had electromagnetic waves interacting with material objects, and then if the apparatus behaved the rules of quantum mechanics, then the rules of quantum electrodynamics were then a necessary consequence. That is what Bohr and Rosenfeld established. So what I'm trying to do today is to discuss the same problem for gravitation. That's where this all starts. So how about gravitation? Is it in fact like electrodynamics? In electrodynamics, of course, we have the classical theory of Maxwell, and we have the quantum theory, which started with Einstein, the theory of the photon, which is the particle of electromagnetism. And the two things, the classical and the quantum picture, are linked together by this subject, which is called quantum electrodynamics. Does the same thing hold for gravity? That is the big question which we don't yet know to answer. And there's been a great deal of talk, a great deal of philosophizing, and not very much detailed science, and I shall try to talk about the detailed science today. In the case of gravitation, you have the classical theory of Einstein, the general relativity, which describes gravitation beautifully as a classical phenomenon in the classical world. Waves of gravitation propagating through a universe with equations which have enormous elegance and enormous predictive power, and has been verified by observation. So it's a firmly based classical theory. On top of that, you have what's called quantum gravity, which is the notion that actually there exists a particle called the graviton, which has the same relation to classical gravity as the photon has to the Maxwell theory. But there's no observational evidence for that. Do gravitons actually exist? We don't know. Nobody has ever seen a single graviton. So that's the subject which I'm going to discuss. Roughly speaking, there are three possible alternatives which might describe the universe we live in. There's first of all what I would call the orthodox view, the view of all the experts, which is that quantum gravity is a good theory, just like quantum electrodynamics, that in fact there do exist gravitons and that they obey the equations of quantum gravitation, quantum gravity, and they have the same kind of behavior as the photon, except that it's harder to observe. So that's the first possibility. The second possibility is what I call concealment, which is that quantum gravity exists, but it can never be detected in the same way that the quark exists, that there's a particle called the quark, which everybody believes is real, but it can never be observed. That has turned out to be a very fruitful concept in particle physics, what's called quantum chromodynamics, which is the theory of the strong interactions, which is based on quarks. So the quark is this quantum field which has all the properties of a quantum field except observability, that in point of fact you can never see a quark by itself. All you can see is confined systems in which the quarks are hidden. That's why we call it confinement. So that's the second possibility. So quantum gravity is real but unobservable. And the third possibility is that quantum gravity is nonsense. That in fact there is no such thing as quantum gravity, that gravity is a purely classical phenomenon, and the alleged effects of quantization are just all of them for some reason absent. So it means that if that were true, gravitation is a classical phenomenon. It is some kind of statistical property which only belongs to matter in the large, not to matter in the small. So there's no such thing as the gravitational field of an electron, that in fact it's only a collective property of matter in bulk. So those are the three possibilities. And the question is, which I'm asking, is what is the evidence? What can we actually say from what we have observed? And that's what I'm going to talk about. So there are actually four subjects I'm going to discuss, which are first of all, the Bohr-Rosenfeld argument. What happens if you actually try to apply the Bohr-Rosenfeld argument to gravitation? So that's the first question. So that's essentially, that's just mathematics. It has an interesting answer. And then the second subject is a particular kind of gravitational observation, which is actually being done in the real world, which is called LIGO. LIGO stands for, what is it called? Laser Interferometry Gravitational Observatory, I guess. Anyway, it's a long vacuum pipe with a mirror at each end and light bouncing up and down, up and down, up and down. And you measure very precisely the phase of the light as it comes back and forth and is reflected at the mirrors. So that's a very precise measurement of the distance between the two mirrors. Well, when a gravitational wave comes by, the gravitational wave is a distortion of the space, so it produces a very small change in the separation of the mirrors as it was measured by the light. So this is a detector for gravitational waves coming by. So the purpose of the apparatus is actually to detect classical gravitational waves coming from astronomical sources. If you actually look at the history of this apparatus, it's not very glorious. The apparatus has been working now for quite a number of years, 5 or 10 years, and it's never seen anything yet. There's always a hope that it will. And they're going to upgrade it in the hopes that they can improve the sensitivity by a factor of 100. And with luck, there will, in fact, be a detection of a classical gravitational wave. That will be a big event. But the question I'm asking is, what about an apparatus of that kind? Could it actually detect a graviton? And the answer is no. So that's my first piece of evidence, that in principle, that kind of an apparatus would be incapable, even if it were as sensitive as it is possible to be, and even if the universe were totally quiet with no background of incidental noise, it would still not be possible to detect a single graviton. So that's quite a strong statement. That's evidence in favor of unobservability of gravitons. The third subject is another kind of detector, and that is a detector consisting of a single atom. That's the analog of Einstein's photoelectric effect. Einstein invented the photon by considering what happens when an electromagnetic wave knocks an electron out of an atom. So you can ask the same question about gravitational wave. Suppose a gravitational wave hits an atom, also can knock out an electron, or it can knock out a proton or a neutron. That also could be observed. So that's another kind of graviton detector. And the answer there is maybe. You can't prove that that doesn't work, but there's fairly strong evidence that it doesn't work. And the fourth subject I will discuss is another way of detecting gravitons, which is based on the coherent conversion of photons into gravitons, which is an interesting process invented by a Russian called Gerzenstein. So here's the reference to Gerzenstein on the board, 1962, so it was an old paper, Wave Resonance of Light and Gravitational Waves. So what Gerzenstein showed is that in classical gravitation electromagnetic theory, there is this process of conversion of gravitons into photons or photons into gravitons, which you can calculate, which gives you a method of detecting gravitons, if this actually happens. It's rather like the oscillation of neutrinos, which was recently discovered, that there are 3 different kinds of neutrinos, and they also can convert into each other by the same kind of coherent process. So it happens whenever you have a linear field, or rather 2 linear fields which satisfy a bilinear coupling equation, so they can convert coherently one into the other. So that's another way of possibly detecting gravitons. So I'll also discuss that. So there are altogether 4 different arguments, and in the end, the question remains open. Well, let me get down then to some of the details. So I guess the first equation is number 10. This is the Bohr-Rosenfeld argument. So what Bohr and Rosenfeld were talking about is the uncertainty relation for observations of electric and magnetic fields, showing that they had to be consistent with quantum electrodynamics. So delta Ex is the uncertainty of a measurement of electric field in some space-time region 1, and delta Ex2 is the uncertainty in the measurement in another space-time region 2. And those two, there's this Heisenberg uncertainty relationship, which says the product of the uncertainties of the two measurements is at least as great as this quantity on the right, which is a purely classical quantity. And A12 is the electric field averaged over region 1 induced by a classical dipole in region 2. And A21 is the other way around. It's the classical dipole in region 2 induced by a dipole in region 1. So you take those two classical dipoles, subtract them, and that gives you the uncertainty in the measurement. So that was the result of the Bohr-Rosenfeld argument, which was a very sort of a verification that quantum electrodynamics had to be true if the classical apparatus you use for the measurement obeys the rules of quantum mechanics. Well, how about it? What happens when you apply that to gravitation? It all looks, the mathematics looks much the same. You have a similar sort of an equation you can write down with the uncertainty of measurement of gravitational fields with classical gravitational dipoles and or quadrupoles in this case. So it looks as though it should be the same. But if you look at Bohr's argument, if you look carefully, you find there's one place where it's very tricky. The argument, in fact, requires a particular physical device, which is the compensation of the induced currents and charges. That Bohr is imagining you have these classical charges and currents, which are the measuring apparatus, and so they move in response to the electric field that you're measuring. But of course, when those classical charges move, they in fact induce then further fields which you cannot control. Those are the fields you're trying to measure. And that messes up your measurement. And in order to make the measurement as precise as possible, Bohr imagines that those induced charges and currents are compensated. So you have another set of charges and currents exactly opposite to the ones you're using for the measurement, which compensate these fields that you're trying to measure, which enables the measurement then to be as precise as it should be. So that compensation requires that you have this other piece of apparatus which carries charges and currents precisely opposite to the ones you're using for the measurement. Well, that you cannot do with gravitation. In the case of gravitation, you're using masses. You have to use masses to induce the gravitational forces that you're trying to measure. But there's no such thing as a negative mass. So this kind of a compensation cannot be done. So that just for that reason, the Bohr-Rosenfeld argument fails. So that's that's the end of chapter 1. So the Bohr-Rosenfeld argument simply doesn't apply to gravitation. So it may be true that quantum gravity has the right commutation rules, or it may not. But you can't prove it as Bohr did for the Maxwell equations. Well, now the second subject is the LIGO. And here I can actually prove a theorem. That's the only really strong statement I can make. It is actually a theorem that a detector of the design of a LIGO, that's two mirrors measuring the gravitational wave as it comes by. cannot in fact work for a single graviton. So here is the argument. It's based on equations, I'm sorry to say. But anyhow, so if you look at the energy density of a gravitational field, this is the equation 1, which if you have a gravitational field in which omega is the frequency and F is the fractional change in the metric. That's the fractional change in distance that's measured in consequence of the distortion of space by the gravitational field. So F is a pure number. It's just the fractional expansion or gravitation, or expansion or contraction of the space measured. Then the energy density of the wave is given by this formula with the square of the velocity of light c and the Newton's constant g. And the remarkable thing there is this square of the speed of light which comes in, which is an enormous factor. So it says that a very, very small distortion of the space produces a large energy density. So the exchange ratio between the observed distortion and the energy it takes is very large. The second equation is for a single graviton. If you take a graviton, which is frequency omega, it'll have a certain energy density which you can calculate. It carries the energy of a graviton is just h omega by according to Planck, and the volume if it has a wavelength which is c over omega. So the cube of the wavelength is roughly the volume of it's the minimum volume that the graviton could occupy. So the energy of a graviton is at most this quantity E sub s. So then if you put those two things together and you say 1 is equal to 2, then you're talking about the energy density of a single graviton, or the distortion of space corresponding to a single graviton. It's this quantity F in equation 3. And the quantity which comes in there is the Planck length. L sub F is the Planck length, which is, because again of this large velocity of light, the Planck length is a very, very small number, 1.4 times 10 to minus 33 centimeters. So that is, in fact, then the standard distortion produced by a single graviton. It's the fact that that's so small which makes gravitons hard to observe. So you see the logic is very simple. So if you wanted to disturb a single graviton, we would have to measure the separation between these two mirrors with an accuracy which is equal to delta, which is just proportional to the Planck length and nothing else. Well, now comes in quantum mechanics for the apparatus. That if you, the apparatus is just the mirror, which has a mass capital M. So you look at equation 6. That's the consequence of quantum mechanics, that if you have a mass capital M, and it has an uncertainty in position, and it also has an uncertainty in velocity, as a consequence, if you try to hold it still for a length of time t, it will wobble around. It will have quantum fluctuations which are of order delta, and that's the equation for the quantum fluctuations of the mirror. So m delta squared is at least Planck's constant times the time. So that's the best you can do for determining the position of a mirror over a time t. And the time t is at least the time it takes just for the light to go from one mirror to the other, which is equal, at least the wavelength of the graviton you're trying to observe. So if you put those equations together, it's 5 and 7, I guess, just the definition of delta, the precision you have to reach, and the quantum mechanics. The answer comes out that the distance between the mirrors has to be less than gm/c squared. So Planck's constant had disappeared. You have just an equation or inequality for the separation of the mirrors. The mirrors have to be close together depending only on their mass to make the measurement possible. And if you look at what that tells you, this quantity on the right, gm/c squared, is just the Schwarzschild radius corresponding to the mass of the mirror. So it's the radius of the black hole of that mass equal to the mass of the mirror. So if the mirrors are that close to each other, it means that each is attracted to the other with an irresistible force, and they both collapse into a black hole. So that's what nature does to prevent you making the experiment. Nature forbids the experiment by this very crude mechanism of forcing you are forced to make the mirrors so heavy to make the quantum fluctuation small that they collapse into a black hole. So in the end, it turns out that you can actually prove mathematically that the apparatus is not going to work. This argument so far assumes the mirrors are just suspended in space as free objects. In fact, that's the best you can do. The alternative would be to have them supported by some kind of elastic framework, but then it has to have a finite sound speed in the mechanical framework. And then if you take a mechanical support, you get equations of the same kind with the sound speed replacing the light speed. So that actually makes things even worse. So if you have a mechanical structure supporting the mirrors, in fact, you get an even stronger inequality. Gm/c squared is greater than the ratio of light to sound velocity times the separation. So that's even worse. So that the conclusion is still true. So you can prove that there is no possible gravitational wave detector of that kind which will detect single gravitons. Well, let's go on then to a more hopeful kind of gravitational wave detector, which is the single atom. That's just the Gravito-electric effect. Now we're looking at a single atom. Gravitational wave comes in. Another particle, either an electron or a neutron or anything else, is kicked out. Well, you can calculate then by quantum mechanics the rate at which this will happen. So here's the calculation. So you're looking at a quadrupole wave. The gravitational wave is a quadrupole. So the matrix element for, this is equation 11, is the matrix element for transition of the electron from state A to state B. So psi A is the wave function of the initial state. Psi B is the wave function of the final state. And X and Y are just the two coordinates of the electron at right angles to each other. So that's a particular quadrupole with polarization at 45 degrees to the X and Y axes. It doesn't matter. You could take the other polarization. It would give the same result. Then the cross-section for the kicking out the electron is given by equation 12, which is this standard formula from quantum mechanics for a quadrupole radiation process. So you have a lot of numbers in front. G is the coupling constant of gravitation, which comes out of the Einstein equation. Again, omega is the wavelength, c is velocity of light. D is this matrix element, and then you have a delta function for energy conservation. It says the graviton energy, h omega, is equal to the difference between the two state energies. So that's the cross-section. Well, that's, of course, a complicated thing to calculate. Doesn't look very promising, but you can make a very strong argument by writing down an exact sum rule. A sum rule in quantum mechanics is a wonderful device for getting simple consequences from complicated equations. You just sum over all the frequencies and everything comes out very simple. So this quantity S of A is the logarithmic average of the cross-section, averaged over energy, but with the divided by d omega over omega. So it's averaged over the logarithm of the energy. So it's the logarithmic average of the cross-section. And that you can calculate very beautifully from this formula. If you integrate over omega and the delta function disappears, and you get just then products of matrix elements which become matrix products. And in fact, you get a double commutator of this quadrupole with the Hamiltonian. And so everything becomes simple. And in the result is S of A, the logarithmic average cross-section, turns out to be just this quantity 14. And that's an exact sum rule. It's a very, very simple but powerful equation. And this capital Q is then a property only of the initial state. The sum over the final states has disappeared. That just gives you a matrix product. So you get just the expectation in the initial state of this differential quantity. And the amazing thing is that all the constants have disappeared, that the mass has disappeared, the potential has disappeared, so the charge of the nucleus has disappeared. It no longer depends on anything except just the shape of the wave function and nothing else. So this Q is a pure number. And if you take the simple case where you're talking about a spherical wave function, that's just an ordinary bound state of an electron in an atom, which you'd expect to be the one which would react most strongly to gravitation, that then everything becomes absurdly simple. And you can then prove just by simple algebra that this capital Q, this coefficient here, is at least 3/4. So it's a number of the order of 1, which is at least 3/4. And if you take a simple model for the wave function, which is so typical of a strongly bound particle, like a ground state of an atom or a ground state of a nucleus. So r to minus n, where n is some positive power times an exponential. That's a typical wave function for a bound particle. Then q is 1 minus n over 6. So it's very close to 1. So that this q, in fact, is just a number which is for ordinary atoms and nuclei close to 1. And the final result of this whole discussion is then that the logarithmic average of the cross-section, equation 14, is just equal to the Planck length squared, and that's all it is. Well, the Planck length squared is a very, very small area of the order of 10 to minus 65 square meters. So there's nothing you can do to change that. It doesn't matter what kind of an atom you're using or whether you're talking about nuclear forces or electromagnetic forces. the best you can do is a cross-section 10 to minus 65 square meters. So if you consider sort of to be, I can't any longer prove a theorem. I can't say this measurement fails for reasons, sort of for fundamental physical reasons. I say it fails just for practical reasons, that if you're looking at the sort of anything that's even conceivably practical, if you had a gravitational source, well, let me just talk about gravitational thermal generators. That's an interesting subject in itself, and I won't spend long on it. That was worked out by Steven Weinberg a long time ago. How much gravitational radiation is actually being produced in the sun? The sun is a wonderful source of gravitational gravitons with observable energy. If you take a collision in the core of the sun, where the average energy of the particles is of the order of 10 kilovolts or so, then so you have mostly electrons and protons colliding together all the time, very hard. They will be generating gravitons, and that's about the best source of gravitons that you can imagine. It's producing huge numbers of gravitons all the time, and they all get out, they all escape from the sun, because the sun is transparent to its own gravitons. So in fact, that's by far the best source of gravitons you can imagine. And that turns out to be 79 megawatts for the sun. Of course, it's a large amount of energy by human standards, but very small by astronomical standards. And so it turns out 4 times 10 to the minus 4 gravitons per centimeter squared per second. And if you multiply that by the cross-section, and imagine the whole Earth is used as your gravitational wave detector, then during the entire lifetime of the sun, you should, on the average, detect 4 gravitons. So it's just barely possible. Anyhow, that's not very encouraging. You can imagine better sources than the sun. You could imagine moving around the universe looking for better sources of gravitons. So there are things like hot neutron stars, which are much more actively radiating than the sun. They have very much higher average thermal energy. So they radiate maybe 10 to the 10 times more strongly than the sun, but they don't live so long. The total amount of energy in the form of gravitons is not all that much greater. The amount available is roughly the same, whether it's the sun or a neutron star. In the case of the neutron star, it comes out faster, but you don't gain all that much. And of course, you can imagine a detector which is bigger than the Earth, maybe closer to the source. So in principle, maybe you could do somewhat better, but not very much. And so that at the most you get perhaps 10 to the 10 gravitons could be detected during the lifetime of the source. And then there comes the argument about backgrounds, that any source of gravitons of that magnitude producing gravitons of the kilovolt range also produces neutrinos. And the neutrino background turns out to be enormously larger than the gravitational flux. The neutrinos have, of course, enormously stronger interaction than gravitons by something like 20 powers of 10. And so they're emitted in much more copiously. And also the detection probabilities for neutrinos are also much larger. So you get something like 30 powers of 10 favoring neutrinos against gravitons. So any conceivable graviton detector looking for thermal gravitons has to deal with this overwhelming background of neutrinos. So from a practical point of view, that seems to make the thing pretty hopeless. But it's not the same, it's not so satisfactory a conclusion as you had for the LIGO. Well, the final set of detectors, which I'll talk about very briefly, are the coherent detectors, that's non-thermal detectors, which are then the thing that Gerstenstein proposed 40 years ago. That comes from this process of coherent conversion of gravitons into photons. So here are the equations governing that. This is the coupling, this first equation, 24, is just a coupling of the gravitational field amplitude, which is the Hij, which is the Einstein tensor, multiplied by the electromagnetic energy tensor. So capital Tij is the electromagnetic energy tensor. And that is then a combination of a classical magnetic field, capital B, and the quantum magnetic field, little b. And so you get a mixing of classical and quantum magnetic fields. So the interaction finally gives you a bilinear term, linear in gravitation and also linear in photon field, multiplied by the classical background field. So now you imagine your detector consists of a long magnet with a strong classical magnetic field, and you put in photons at one end, and out come gravitons at the other end, or vice versa. And the beauty of that is that since the process is coherent, the probability of conversion goes as the square of the length. So the probability of conversion is actually this equation 29. Says probability of conversion is b squared, the square of the magnetic field, times d squared, which is the length of your magnet, divided by this fourth power of the velocity of light. It's always the velocity of light which kills you. So the probabilities are amazingly small. And again, this is a purely classical effect. Planck's constant has disappeared. It's a classical mixing of gravity with photons. And the conversion length, capital L, is 10 to the 25 centimeters, which is of the order of a kiloparsec in astronomical units, 10 to the 25 centimeters, divided by the magnetic field in Gauss. So it means for any conceivable magnet, the probabilities are very small. But still, again, it looks as though in principle it might perhaps be feasible. But then there comes a fatal flaw into this argument too, that nonlinear electrodynamics. It turns out that the Maxwell field, after all, is not linear. And this was, in fact, the discovery of Euler and Heisenberg already in 1936. It's one of the most beautiful things that Heisenberg did when he was still a scientist. And they worked, and he and his student Euler worked out the theory of the polarization of the vacuum produced by pair creation, that is, electrons and positrons popping up and down in the vacuum, produce this fourth order term in the Maxwell equations. So the Maxwell equations are inherently nonlinear when you allow the Maxwell field to interact with electrons and positrons. So this is the Euler-Heisenberg nonlinear electrodynamics, which tells you that, in fact, the speed of light in a classical magnetic field is less than it would be in a vacuum. And so this final equation 35 It's the amount that the speed of light is reduced in a magnetic field. So B is the classical magnetic field. Hc is the critical field, which is 5 times 13 Gauss, 10 to the 13 Gauss, which is actually about what you get astronomically in a pulsar. A pulsar is a magnetized neutron star, which typically have fields which are just about equal to the critical field. So this, in a pulsar, these numbers can be quite large. The Maxwell field really becomes strongly nonlinear. And that tells you then this coherent conversion doesn't work. That if you have graviton and a photon going at different speeds, they're not going to be coherent with one another. So the coherent conversion simply fails. And so that happens then to be true in a neutron star. And also if you imagine a detector in which your magnetic field is more of a reasonable terrestrial magnetic field of the order of 10 Tesla or something of the kind that was used. By the way, the people at CERN actually used this as a device for detecting axions. There was an experiment done at CERN looking for the coherent conversion of photons into axions, axion being a hypothetical particle with mass 0, which might exist and be detectable in this way. And so they did the experiment and also got a null result, because they were not looking for gravitons. But if you took an experiment of that kind with an unreasonably long magnet of the order of, say, 100 million kilometers or something of that kind, still it turns out that the coherent conversion doesn't work. The nonlinearity of the Maxwell equation is enough to defeat you. So it seems that this kind of detector also doesn't seem to work. Anyway, I'll leave the subject there. I don't want to get drowned in details. But so the final conclusion is that the possibilities remain open, that quantum gravity may be in fact correct, as everybody, all the experts believe, or it may be correct but with confinement, so that gravitons are always confined and not visible. Or it may be that gravitons don't exist. So we can't yet decide that. But I think it's an interesting subject, and certainly there's a possibility of pushing these arguments very much further. Thank you.